using nested plots and analyzing frequency data. Why does plot size matter? Frequency estimates are directly related to the size of the quadrat or the plot that's used for measurements. As you may recall, frequency is defined as the number of times a plant species is present in a given number of uniformly sized quadrats that are placed repeatedly across a stand of vegetation. The definition of frequency includes specifications about the size of the quadrat. So not only are we concerned with presence and absence, but also making sure that we use uniformly sized quadrats when we are estimating frequency. So let's see how this works by examining this simple population of plants and looking at the estimate of pink daisy using 3 different size quadrats. We see that as the quadrat size increases, the frequency estimates increase from 0% to 50% to 100% with the largest size quadrat. And this makes sense that frequency estimates are going to increase as we increase quadrat size, because larger plots simply cover larger areas, and therefore we have a greater likelihood of including or encountering species with larger size quadrats. Now you may be wondering why you should care about this. And basically it's because frequency data are different from the data that we've seen before because they are discrete. They're simply presence, absence, they're binomial data. And so they follow a binomial distribution. And therefore, in order to have sensitivity to change of the vegetation, we have the greatest sensitivity when frequency estimates are between 40 to 60%. We still have very good sensitivity in the range between 20 to 80% frequency. And so we usually state that as the desired range that we want our frequency estimates to occur in. However, frequency changes, we're not sensitive to frequency changes when the frequency estimates are in the lowest or the most extreme ranges. So between, if they're less than 10% or greater than 90% frequency, we're not able to discuss changes over time or comparisons between areas. So we try to avoid using quadrat sizes that are going to produce frequency estimates in these extreme ranges. So let's talk about how we do go about determining the correct plot size for individual species. Well, what we do is we repeatedly estimate frequency using increasingly larger quadrats, and we estimate the frequency for the species that we're interested in. Now, we don't actually go out with different size quadrats. Instead, we use a nested quadrat to do this. And this is simply a frame that we have marked, or sometimes we will actually have hard edges in there, but we can mark the dimensions of the larger, successively larger quadrats in these frames. So let's take a look at the data that we would get in this example. Grass species is the only species that occurred in the smallest quadrat size 1. It occurred in 2 out of 5 quadrats for 40% frequency. As we increase the size of the quadrat, the frequency of grass rapidly increased to 100%. With the daisy, the yellow daisy, it was not found in the smallest quadrat, but it started to occur in the second largest quadrat, or quadrat size 2, for 20%. And we see that as we increase the quadrat size, the frequency of the yellow daisy increases from 20% to 60 and then 80%. We also see that for the white flower and clover, the two smallest size quadrats did not pick up either one of these species, but we did start to encounter them with the third and the fourth largest quadrat for between 20 to 40% frequency for the white flower and 40 to 60% frequency for the clover. So what we try to do is select the appropriate plot size for each species, and when we compare frequency to look for vegetation changes, we always do this on a species by species basis. It's important then that we maintain the same plot size over time when we measure frequency for individual species, and then we can only compare changes if the same plot size was used consistently for an individual species. Where we run into trouble is that vegetation is going to change. That's why we measure frequency in the first place. And so what do we do if there is a change in the vegetation and the quadrat size that was appropriate is no longer ideal for the species that we are measuring? Well, we have to adjust the quadrat size. And this requires us to know that the frequency is changing so that we can measure the frequency of the species in the original size quadrat and in the new quadrat size so that we are able to compare them. This allows for continuity in comparing frequency estimates over years when the quadrat size had to change. There's a problem with this though. First of all, it does take time, and it also assumes that we know that we are near a threshold size for a species and that we would measure it with two different size quadrats out in the field. Oftentimes, we aren't going to know that we've recorded a frequency in one of those extreme ranges below 10% or above 90% until after we've taken the data and gone back to the office. So how can we deal with this? Well, one thing we can do is we can use nested plots, and we can measure the species in all of the plots as we're taking frequency data. So what we see here is a nested quadrat that is broken into 4 different sizes. The smallest is the red, and then the second smallest is the green. The third size is a rectangle, which is twice the size of the plot 2, and then the entire frame is plot 4. And what we do is we record frequency as the occurrence in the smallest plot. So let's take an example and look at this clover. There's only one plant in this nested plot, and we see that clover does not occur in plot 1, so there's not a hit there, but it does occur in plot 2. Now, because it occurs in plot 2, it also occurs in plot 3 because plot 2 is included in plot 3. So we have one hit on clover in plot 3. And the same is true for plot 4. Plot 2 is included in plot 4, and so we have one hit on clover in plot 4. This is a dynamic approach that facilitates comparison even if the plot sizes need to change. So let's take a look at how this is done in action. Here we have 4 different nested plots, that plot A, B, C, and D, and we've got just a very simple system with only 2 species. What we record is the smallest plot that a species occurs in. So for plot A, the smallest plot that the clover occurs in is the plot size 4, but for the grass it occurs in plot size 1. In sample B, the clover occurs in plot size 3, but the grass occurs in plot 2. In C, the smallest plot that clover occurs in is 3, whereas the grass occurs in plot 1. And in sample D, the smallest quadrat that the clover occurs in is plot 2, and grass is found in plot 3. When we look at how we then do the calculations here, we take a plot-by-plot analysis. Using plot 1, we get, for grass, we have an estimate of 50% frequency, but an estimate of 0% frequency for clover. What we see by doing this is that we can identify the quadrat sizes that give us our estimates of frequency in the acceptable range. So for clover, plot size 2 and 3 give us acceptable estimates of frequency at 25 and 75%. For grass, plot sizes 1 and 2 give us estimates in the reasonable range. Now, of course, we would not make these assessments using only 4 quadrats, but what this tells us is that for now we could actually use just one size quadrat, plot 2, to estimate both clover and grass. So let's talk about how we analyze and interpret frequency data. Remember, we use frequency data to assess vegetation change either at one site over time or between sites. And we always do our comparisons on a species by species basis. We want to make sure that we compare frequency changes within species and not between species. There are 2 common statistical approaches that we use because the data are discrete and have a binomial distribution. One is binomial confidence intervals, and the second is the chi-square analysis. Now, a binomial confidence interval is like other confidence intervals that we've seen. They are based on a desired confidence level, knowing what the sample size was and what our estimated frequency was. We calculate the confidence interval by using the square root of P times Q over N, where P equals the proportion of plots that contained the species, and Q is 1 minus P, or the proportion of plots that without the species, or in which the species was absent, and then N is the number of plots observed. So let's look at an example of blue grama frequency data that was measured in 2 years using 200 quadrats. In this case, in year 1, the frequency was 34%, as written as a proportion, that's 0.34, and in year 2, the frequency was 40%, written as a proportion is 0.4. And using confidence interval tables that are available for N equals 200, we were able to determine that the confidence intervals are between 27 to 41% for year 1 and 33 to 47% for year 2. We would interpret this to mean that the frequency of blue grama did not vary between the years because the confidence intervals overlap, and any differences that we see could simply be due to sampling error. Let's look at chi-squared analysis. With a chi-squared analysis, what we do is we compare our observed values to expected values. And we are testing a null hypothesis that there is no difference between the observed frequencies. So again, these can be frequencies taken at one site over different time periods or between 2 different sites. And so we use a 2x2 contingency table in which, in this case, we're looking at years, comparing years. We have the observed presence of species and the observed absence of species. And then we calculate what is expected. I'm not going to go into the details of calculations as that is covered very well in the learning guide. And we use the chi-squared formula where we develop a chi-squared statistic and then compare that to a critical chi-square statistic from a chi-square table. So let's take an example. Again, here we're looking at the example we had before with blue grandma in year 1 and year 2. In year 1, we had 34% frequency of blue grandma. Remember that that was measured with 200 quadrats, and so the number of quadrats in which it was present was 68. The number of quadrats in which it was absent was 132. In year 2, we had 40% frequency, so the number of quadrats in which it occurred was 80, and the number of quadrats in which blue grandma was absent is 120. We use the approach to determine the expected values and then follow the guidelines to calculate a chi-squared statistic. In this case, we see we have the observed minus the expected. That quantity is squared, and then it's divided by the expected value. We do this for the present and in year 2 and in year 1, and for the absence in year 2 and year 1. That condenses down to the 0.49 twice plus 0.29 twice, and our chi-squared statistic is 1.56. We then compare our calculated chi-square statistic to a critical chi-square value from the chi-square table, which is 2.706. Since 1.56 is less than 2.706, we do not reject the null hypothesis. This means that the frequency of blue grandma did not change between year 1 and year 2. So to conclude, frequency estimates are greatly affected by plot size, and the sensitivity to change in the vegetation is best when the frequency estimates are between 20 to 80%. We need to use the appropriate plot size to keep frequency estimates in this range, and if necessary, we will use nested plots in order to do that. We then compare our estimates of frequency using chi-squared analysis or binomial confidence intervals.